Hello students, this is Shakil and today we are going to discuss work, power and energy from AS Physics. Well, this is the second lecture for this topic, second and the last one. And in this lecture, we are going to cover something about gravitational potential energy and kinetic energy and their mutual relationship. So first, we'll study about gravitational uh, potential energy inside uniform gravitational field, and we will use and apply this formula in different situations inside the uniform gravitational field. And then we will look upon kinetic energy and its derivation, half mv square, and we'll use it. So first of all, let's talk about mechanical energy. Mechanical energy is the energy involved with objects due to movement or changes in position. Based on its definition, mechanical energy is divided in two groups. The first group is the kinetic energy, and the second group is potential energy. Well, the potential energy is further subdivided in two groups. The first one is gravitational potential energy, and the second one is elastic potential energy. There are many other potential energies, but we don't have to study that over here. For example, there is electric potential energy as well. We'll study that in A2. And there is magnetic potential energy as well. But we don't have to study that. We'll study that in A2. Okay, now let's look upon these energies one after another. The first one to be looked at is kinetic energy. Well, kinetic means movement or motion. It's a Latin word. So its definition is ability of object to do work due to its movement or due to motion of the object. We can also define it as energy possessed by moving objects, the simple definition. Its equation is quite simple. Kinetic energy is half mv square, where m is the mass of object and v is the speed of the object. Well, there is another equation which relates kinetic energy with the work done. So kinetic energy is equal to useful work done. Well, what is useful work done? As work is forced into distance, but useful work done means resultant force multiplied by distance. But remember, resultant force. And what is resultant force? It is applied force minus opposing force. So you can find kinetic energy by two ways. Okay, well, about the factors, kinetic energy is proportional to mass if you keep speed constant. Like if two objects of different masses are moving at same speed, the heavier mass would have greater kinetic energy. The second one is kinetic energy proportional to speed square if you keep mass constant. Okay, the next thing is change in kinetic energy is half mv square minus half mu square, or taking 1 by 2m common, it will be v square minus u square. Well, now we have to derive the equation for kinetic energy, which is half mv square. So let's, this is very important part of the syllabus. Let's say there's an object of mass m and it is at rest, initial speed is 0. Then you apply a constant size force on it such that its acceleration is constant and the mass gains a speed of v by covering a distance or displacement s. So work done by this force to move the trolley for this distance, we know that it is work equal force into distance. This is equation 1. Now, we know that this work is equivalent to a change in energy of object, and you know this work will change the kinetic energy of object since object is moving. So we can replace work with kinetic energy. And for force, force is equals to ma, which is from Newton's second law of motion. And for the third thing, which is displacement, question mark. So we have to see what is S equivalent to. So since in this case, acceleration is constant, so the kinematics equation of motion can be used. So as you know that we have U in this case, which is 0, we have V, which is the final velocity, we have the displacement, and we have the acceleration. So we have these equations and the time is missing. So we will select that equation in which time is not there. So that is 2as equal v square minus u square. Okay, now you have to put the values. So the only value that we have to insert is u square, which is the object was at rest. So 2as equal v square, and from here s equals v square by 2a. So now you have calculated value of w, you have calculated value of f, you have calculated value of s. So what we'll do is we'll substitute the values of f, w, and s in equation 1. So you know the equation 1 was work done equal force into distance. So as you know, we have figured out that the work done is equivalent to change in kinetic energy, the force equals to ma, and the displacement from third equation equals v over 2a. So you insert them, a cancel away, so the change in kinetic energy is half mv square since u is 0. Well, if u is not 0, obviously you will stay over there. So it will be half mv square minus half mu square. So that's the derivation. Now, some exam tricks with the kinetic energy. It's very simple, although, but I better thought it to share it with you. As kinetic energy is half mv square, so this m is the mass. So sometimes mass value is not directly given. So you have to use some equations to find its value. For example, density equal mass over volume, and mass equal density into volume. So density and volume will be given, so you'll be multiplying them to get mass of the substance. The second is speed. Speed value must be used in meter per second. Well, if it is given in kilometer per hour, you have to convert that. And we have already done that in kinematics, how to convert kilometer per hour into meter per second. Well, the next thing is potential energy, the famous potential energy. You know, potential, like how much potential you have, it means how much ability to do something you have, how much energy you have. So potential energy is actually the energy stored in object or system due to change in its position from the original position or change in its position inside a field. So based on the definition, it has got two types. The first type is elastic potential energy. Well, elastic potential energy, the energy possessed by objects due to deformation. Let's say you are tightening a spring, you are stretching the catapult, you are stretching a rubber band. So of course you change its position, you deformed it. So due to deformation, object gained elastic potential energy. Well, we'll study that in depth in the next chapter of deformation, but well, as it is energy, so we have to study it over here as well. So elastic potential energy equals force into change in length. Yeah, the force that you applied and how much length is changed due to that force. And it's further equivalent to half F into delta L. Well, that's strange, but yes, that is the equation we'll study in the deformation topic. And then further, it is equivalent to half K delta L square, where delta L is the change in length or deformation. It can be extension or compression. And F is the applied force and K is the elastic constant. It is actually a feature of the material. Well, moving forward to gravitational potential energy now. It's the ability of object to do work due to change in height inside a gravitational field. And remember, we will study GPE in uniform field. So GPE is denoted by EP as well. It is mg delta h. Delta h or h mean the same thing. Well, in some cases, GPE equals to force into distance as well. So let's say we have to derive this whole GP is mgh. Let's say this is a mass m placed on the ground, and then you lift that up to height h. So the work done is equivalent to force into distance, and in this case, when you move object vertically up, the force is equal to weight of object, and distance is equal to the height gained. So weight is mg and height is h. So that's how we can say in a simpler way that change in GP is equal to mgh. Well, there's an important thing. Height is always measured from bottom of the object. Well, as you see in this diagram, it is measured from the bottom of the object, or in some cases from center of gravity of the object. Well, let's look upon some interesting cases now. Inclined plane and GPE. Sometime object is going to move on an inclined plane with a inclination as theta. So we have to find, let's say the object was initially at point P, this is the start point, and then you moved it up to this position, you stop it over there, which is point Q, and you move it for length L, and its weight is W. So what you have to do is you have to find change in GPE between position P and Q. So obviously, change in GPE is mgh. Well, mg is actually the weight of the object. What is h? How much height it has gained? Well, interesting. How much height? So for that, I have drawn it over here. This is the length L which is moved, and this is the triangle, and this is angle theta. So when you resolve L, this component will be L sine theta, and this component will be L cos theta. Okay, so what is height equivalent to? Obviously, height is this, because you have to look for the vertical height. No? So this is the height. So height is L sine theta. So that's how we write it, L sine theta. So you can write it weight into L sine theta, or you can write it mg L sine theta, because you know weight is mg, and mg L sine theta is the change in GP. M is the mass, G is the gravity, L is the length moved, and sine theta, theta is the angle of inclination on the slope. Well, next is change in GP of water in a big reservoir. That's a very important thing. Well, it is interesting as well. Let's say there is a container, like I'm making the outline of the container. This is the container, and it is filled with the water, and water weight is W, which is acting from the center of gravity point, and its height is H. So what's the mass of water? M. What's the weight of water? W, which is mg. And what is the GPE in this water? Well, interesting. GP. So GP is mgh. But I have written mgh by 2. Why? Because we always take the height from bottom to the center of gravity. I have to take you back. I have to take you back to this point. Well, the bottom one. Height is always measured from bottom of the object, or in some cases from center of gravity of the object. Well, at some cases this one. So that's why height in this case is measured from center of gravity point to the bottommost point. That's why GPE stored in the water is mg h by 2. Okay, next thing. Where is an interesting question? This is from the past paper. Well, there's a water with height h, and its weight is, of course, from center of gravity point. So center of gravity is at a depth of h by 2 from the bottom, and then you half fill it. So how much is the GPE lost by the water when you half filled it? Well, when you half filled it, so its GPE, so its center of gravity will become at a distance of h by 4. So in diagram A, the GPE is mgh by 2, and in diagram B, the GPE is mgh by 4. So GP lost is GP in A minus GP in B. So when you do the maths, so the loss in GPE is mgh by 4. Is it interesting? I hope so, and I hope you have understood this. Let's move to next, which is energy conversion cases. We have to look for some cases. This is very important from exam perspective. So there are like 4 to 5 cases. The case A is falling body case, no air drag. This is like IGCSE O-level case. If an object is at the highest point and there is no air and you're going to drop it, it is going to move down, then we say that GPE on top is equal to kinetic energy at bottom. So GP on top is mgh, and kinetic energy is bottom at half mv squared. So m and m are going to be cancelled away on the both sides. Okay, and then you're left with g into h equals half v squared. So delta h, or change in height, is v squared over 2g, or v is 2g h square root. Well, there's example, a mass of the ball is 200 grams, it was at rest, no air, and it was dropped from a height of 250 centimeters. So find the speed with which ball will have an impact with the ground. So you have to solve it yourself. You can pause the video, solve it, and its answer must be 7 meters per second. Okay, so let's move on to case B, which is falling body cases, but in air drag of constant average value. Let's say, usually, air resistance depends upon speed. As the object speed increases, air resistance increases. But in this case, we'll consider that the air drag is having a constant value, a constant average value. So the same case with air resistance. So GP on top is equal to kinetic energy at bottom plus work done against air drag, because air resistance is opposing force. So work is done against air resistance to keep the body moving. So GP on top is mgh, kinetic energy half mv square, and work done against air drag is FD, which is air drag into height. Well, case C is inclined plane case, and there is no friction at the surface is smooth. Theta is the angle of inclination, L is the length that is to be moved by an object of mass m, which was initially at rest at the highest point. So we say that when it is transferred from highest point to the bottom, the GPE at the top is equal to kinetic energy at the bottom, because there is no friction, so no heat losses. So GPE is mg sine theta into L, it is like component of weight in GP is also like work done. So that is component of weight down the slope, which in this case, like if W is here, so when you resolve it, so component of weight down the slope is W sine theta, and the distance moved is L. That's why it is mg sine theta into L. And the kinetic energy is half mv squared. So GP is lost and kinetic energy is gained. So the second case, the last case is inclined plane case with friction. So again, the same thing, but friction is there. So change in GPE is equal to change in kinetic energy plus work done against friction. So mg sine theta into L equals half mv squared plus F into L. F is friction, L is the length moved. Or mgl sine theta equal, kinetic energy can also be written as resulting force into length plus friction into length. Okay, well, there's a tip. In questions related to energy conversion, always use this expression like input energy equal useful output energy or energy plus wasted energy. Well, the input energy is energy at the start of the process. Like when the object is to start its motion, you have to see what type of energy is present over there. And then useful energy, which is energy gained during the process. Wasted is like work done against air drag or against friction. This is actually the dissipated energies, internal energy, you can say, and these are lost energies. Well, if during a process, constant speed is mentioned, then it means that change in kinetic energy would be zero. This is very important. Let's see an example. A car is moving downhill with constant speed while applying a braking force. Write its energy expression. Well, if it is moving downhill, so it means that it is losing GPE. So the change in GP is equal to work done against friction, which is friction into distance. Because its speed is not changing, its speed is constant. So the change in kinetic energy will not be there. So the change in kinetic energy will be zero. Why? Because its speed is constant. It is not gaining or losing any speed. Okay, let's move forward to some graphical analysis of energies in different situations. Let's make some graphs. And the first is when there is no air drag or no friction. So for the falling body cases, like you're going to drop something, let's say this is a ball, and you are going to drop it from a certain height. And what you have to do is you have to make its energy graphs. Well, if there is no air, so the like the graph is between energy and height, then the GPE graph line would be a straight line, and the kinetic energy line would be a straight line of positive gradient. So as kinetic energy GPE at top is kinetic energy at bottom, that's why it would be a cross. So since gradient of potential energy distance graph equals to weight, right? So that's why it would be a cross. Okay, when you make it against time, like energy against time, you know that when you drop an object, its speed keeps on increasing with time. So as its speed keeps on increasing in time, so it means that there is greater change in potential energy as time is passing, because near the ground, the speed will be higher. So it means it would be covering more distance. So that's why the GP graph would be a increasing gradient graph. For the kinetic energy, well, it's the same thing. It would be a positive increasing gradient graph because as time passes, well, speed keeps on increasing. So kinetic energy will increase more. And one more thing to define that is kinetic energy, well, is actually proportional to v square. So as speed increases, kinetic energy also increases, and it increases more because it is speed square. Well, the next thing is falling bodies in presence of air drag. The same thing as previous, but air is there. So again, I've plotted the same graph. The first is energy versus height, and the second is energy versus time. So energy versus height, the GPE line would be the straight line. Potential energy, it will be a straight line since potential energy height gradient gives weight, which remains the same regardless of air effects. And the kinetic energy would be like this because, well, kinetic energy will increase at decreasing rate and until it become constant because the object will again attain the terminal speed. That's why kinetic energy will become constant. And you say that potential energy at top will be more than kinetic energy at bottom because, you know, there are some energy losses against air resistance as well. So this patch is actually representing the work done against air drag, and that is the lost energy actually. Okay, look at the second graph, which is energy time graph. So potential energy graph is like first, it is like increasing gradient and then it is constant. So it is constant at the end. Let's say this red line is the constant line. Why? Because object has achieved terminal speed. So now it is losing the height at constant rate. That's why the graph would be constant. And again, the kinetic energy would be the same because, well, the object is going to attain the terminal speed. And the difference between these two energies is actually the lost energy. Well, there are some useful equations of the chapter. At the end, we just have to recall them. Work is force into distance into cos theta. Work is also equal to area under Fs graph. And then power is work over time, or it is energy over time, or it is FV, which is motive power, or it is IV, which is electrical power. Efficiency is useful output, energy, work or power, supplied input, energy, work or power. And percentage efficiency, you just have to multiply that with 100. Change in kinetic energy is half mv square, or if it is resultant force into distance. And change in GP is mgh, or it is mg sine theta into L for inclined plane cases. I'm going to share the worksheet soon in the group as well, so you'll have to solve those questions. Well, so this is end of the chapter, end of unit, which is work, power, and energy. And I hope that you must got all the concepts. In case of any difficulty or ambiguity, you can contact me on WhatsApp. But remember, you have to watch the video again and again, and you have to make the notes from it. Then you would be able to solve the past paper questions from it. Thank you so much. We'll see you in the next video. And the next video is about deformation. And deformation will have two videos as well, video 1 and video 2, to cover up that chapter. Thank you so much. Goodbye.